Now we are going to see what is channel length modulation, effect of channel length modulation. So what they are saying is channel length. A channel is formed between the two n plus regions, as in enhancement and depletion MOSFET, right? But that channel length is not same throughout. And you see in enhancement, enhancement MOSFET, you see the channel length. It is maximum at the ends, it is minimum at the center. It is dependent on the voltage what you apply, right? And in depletion MOSFET, you see it is wedge shaped. So I cannot clearly predict what is the length of my channel, but my length of the channel is keeping on varying, right? So that effect is called as channel length modulation. Modulation means it is varying with respect to one parameter. What is that one parameter? It is your applied voltage. Okay, whatever voltage you are going to apply, that is going to determine the channel length characteristics. So this graph we have seen, right? This is for enhancement MOSFET. And if you backtrace all the, if you draw a tangent to all the curves, and if you backtrace all the curves, you can see that this, at one particular point, all these graphs will meet. So this is the drain characteristics of MOSFET. And see, for JFET, this will increase and become constant. I hope you remember the same graph. If you draw for JFET, this will be the characteristic. But MOSFET, the graph will be increasing, and they will take a lot of time before they become constant. So these graphs are always increasing, right? So when you take a tangent and when you backtrace all these graphs, they are going to meet at one point. That point is called as minus VA. So we name that point as minus VA. Okay, we'll see about this point now. So you see here a non-zero slope exists beyond the saturation point. So for the saturation region, the effective channel length decreases, and this phenomenon is called as channel length modulation. We have seen a point called pinch off, right? Pinch off is the condition when the channel area is very, very minimum. Here we are not having a very big channel, so we will not focus on channel area. We will focus on what is called as channel length. So in JFET, we call it as channel area because the channel was a very big channel. But here, the channel is very, very small as it is formed between the two n plus regions. Okay. So we will not worry about what is the channel area. We will be bothering about the channel length only. So when you are going to have when you are going to operate in saturation, the channel length is going to be minimum, and the constant drain current is going to flow through the device. Below the saturation condition, the channel length will be increasing. So at one particular point, when you operate the device at saturation, the channel length will start decreasing, and this phenomenon is called as channel length modulation. Modulation, the meaning of the word modulation is I am going to change a parameter with respect to another. What parameter is changing? Channel length modulation is changing. With respect to what? With respect to the applied voltage. Okay, so every term you study in electron devices will have a naming, and the naming you have a reason. You cannot just like this say it is channel length variation. You cannot say this channel length difference. It is perfectly called as channel length modulation because my channel length is varying with respect to the applied voltage. So the drain current, if you calculate the for n-channel enhancement MOSFET, the drain current equation is given by this one. The derivation is not in our scope. In ED, we will not, this unit, all these units, we will not be doing derivations in depth. Only selected derivations will be in depth. Other things, you have to accept the result, whatever is given in the book. So the drain current expression is given by this term, Kn into VGS minus VTN the whole square plus 1 plus lambda VDS. So lambda is called as channel length modulation parameter, or it is same as what we call as 1 by lambda in BJT. In BJT, we have it as 1 by lambda. Here we call it as lambda. Lambda is a positive quantity. Okay. Kn is a conduction parameter. It is a constant. And VTN is a threshold voltage. Okay, so when you expand the curves back, when you backtrace the curves, as I said, at one particular point you make id become 0. This point id becomes 0, right? So when you put id is equal to 0 in this equation, and when you solve for vds, when you put vds equal to minus ve, and ve is going to be 1 by lambda, when you solve this equation, you will get the expression as VA minus VA equal to minus 1 by lambda. So they say that at the particular voltage 1 by lambda, VDS equal to VE. Here they have given VE, in the graph they have given VA. So don't think they are same only. There is typographical mistake. So VE is going to be equal to 1 by lambda. Okay, and this value of V is going to be your VDS. So when you put VDS, see, in this expression for ID, when what all the possibilities for ID to be zero? Can anybody say how all, if ID to be zero, what all the possibilities you have in this equation? You have product of three terms, right? So when will ID be zero? When A into B into C equal to zero, what are the possibilities you have? In mathematics, ABC equal to zero. So what are the possibilities you have? Can anybody say?
Any one should be zero, sir.
Any one
Either
can be zero or any two can be zero, because when all are zero, we don't have a condition for 0 into 0 into 0. We don't know what is mathematically correct, right? The same way here, the product of three terms, either Kn can be zero, but Kn is a conduction parameter. So Kn cannot be zero because conduction is going to happen always. And second case, VGS minus VTN equal to 0 or VGS equal to VTN. I will not operate my device exactly at threshold. I'll be operating the device above the threshold. So this is also ruled out. The only possibility is 1 plus lambda VDS equal to 0. So if it's all 1 plus lambda VDS equal to 0, you will get VDS equal to minus 1 by lambda. That negative value of VDS is called as minus VE in theory, and in graph it is called as minus VA. So this parameter, they say it contributes to channel length modulation, and this lambda is called as your channel length modulation parameter. It has a serious effect on the drain current characteristics, because your channel length is going to determine the amount of current going to flow from your source to your drain, and it is directly related if you see. So when lambda is going to be high, your ID will be high. When lambda is going to be less, ID is going to be less. Okay, so that is the meaning of the channel length parameter lambda. And when you derive the expression, you find that it is exactly at the voltage 1 by lambda, your drain current becomes 0, and you have the effect of channel length modulation. So when the channel length modulation happens, the drain current becomes 0. So definitely you'll have some resistance inside your circuit, correct? When will current become 0? When there is a large resistance inside your circuit. The only resistance can reduce your current, right? So that current of the resistance relating to channel length modulation is given by R naught is equal to ID by VDS. Okay, ID by VDS at constant VGS. This is actually going to be inverse. Okay, it is going to be inverse because resistance, it is voltage by current, correct? So here they have given ID by VDS. It is actually after taking ID by VDS differentiation, you have to take inverse for that. See here, they have given the minus sign. So here also you will have this minus sign coming, because our resistance is voltage by current, correct? Here they have given current by voltage. So finally you have to take an inverse. And you have the expression for ID and VDS. ID in terms of VDS, differentiate that. See, these two terms are constant, so they will come as it is, Kn into VGS Q minus VTN the whole square. If we differentiate with respect to VDS, it is just lambda. Okay, differentiation of 1 to 0, it is just lambda. And I can write this VGS as VGS Q. It is the Q point. And now I am substituting the expression for the Kn into this one. So Kn into this one is equal to IDSS into 1 minus VGSQ by Vp. This is your usual drain current equation what we have from JFET, right? So ID is equal to, from JFET you have this equation, right? ID is equal to IDSS into 1 minus VGS by Vp the whole square. So the same equation I'm going to use it here. IDSS into 1 minus VGS by Vp the whole square. So I'm going to use that equation here for simplification. And if I simplify, I am considering this entire equation IDS is into 1 minus VGS by VP the whole square as a single term IDQ. So my R naught will be equal to 1 by lambda IDQ. And 1 by lambda, it is VE. So R naught is equal to VE by IDQ. So this output resistance will be seen in the equivalent circuit of the MOSFET because of channel length modulation. Okay. See, wherever Q comes, it is called as Q point. There is a Q point uh, for all the transistors, and you have to operate the device only at the Q point for using it as amplifier. So அந்த இடத்துல தான் to differentiate from the other voltage, we'll be suffixing Q. So VGS, the normal VGS. When I put VGS Q, it is at that exact Q point. And here also you see it is not ID, it is IDQ because I'm going to operate the device exactly at the particular current ID at the Q point. Okay, Q point it defines the active region of your transistor. I told you, right? Only in the active region you will be uh, only in the active region you will be using your transistor as an amplifier, right? So wherever this Q comes, you understand that the Q point we will be studying more in your next semester electronic circuits. So you will be studying more about the Q point. For now, understand Q point means it is the point which determines the values for VGS, VDS, and ID. And at Q point, the transistor is fit to be used as an amplifier. The why we are studying so much about channel length modulation is this parameter R naught, which is a result of this channel modulation, will be seen in the will be coming as the output resistance in the equivalent circuit for MOSFET. So when we study equivalent circuit for MOSFET, this R naught will be coming there in the output side, and you have to relate that this R naught is because of channel length modulation parameter. Okay, at the time you should not blink why this R naught is coming. It is only because of channel length modulation effect in your MOSFET. Okay, so we are going to stop here for the day. So any doubt so far in today's class, you can ask now.